Guys, so we start. Now we will have lessons from industry, from real life.
Okay, it works. Hey guys, um, this is actually quite weird setup, so I probably will spend first 10 minutes like turning around until I find the right place to stay. But to get started, thanks Evgeny for inviting me here, and Evgeny and the organizers asked me to talk a little bit about how you use machine learning in industry versus academia, right? And it was like sort of, if I can share any lessons of how to use it in industry versus academia. And actually it's impossible to do without telling you about this sort of whole, life and ecosystem of industry and how it's different from academia. So I have probably like 30 slides in the deck. There is no goal to go over all of them, so we can stop at any time. There's no formulas there, just pictures, right? You will also feel a little bit of, consulting feel in there because there's like a lot of sort of structured information presented. Again, I'm not gonna read slides, you're gonna just talk around them and feel free to, stop, interrupt, ask questions if there's anything that interests you. Why Evgeny asked me to do this? Well, because actually, I started my career back, I graduated from Moscow Engineering and Physics Institute, then got PhD University of Utah, then was a postdoc at Caltech, spent some time doing academic research, then worked for Data Science Lab, then worked for Yahoo, in other companies in Silicon Valley, built my own startup, and within the last 4 years, I'm running in Moscow consulting team within Boston Consulting Group data science team. And so out of various industries, I pretty much have seen a lot, and so I can probably share with you some of the experiences. But again, it's a huge topic, so feel free to stop me and sort of direct me if there's any particular interest here in the audience, okay? Before we get started, right here among you guys, who actually works for industry now? Oh, okay. I somehow thought that there was like more academicians here, but anyway, good. Now, who is considering to work for industry, but kind of not sure if that's the right place? Okay, guys, I think for you this will be the most interesting discussion, right? So you would kind of see the differences and can contrast them. So first of all, industry versus academia, and when somebody, especially from computer science, says industry, the first thing that comes to mind would be what? Would be Google, Facebook, Yandex, all those companies that are digital companies, right? Sort of new age companies. I'm gonna talk more about sort of real world companies, the companies that are from the real sector, FI, et cetera, et cetera. So those places where you can actually that deal with physical world and where machine learning is more of applied subject. Now, I don't pretend, or I don't want to say that this is exhaustive, but this is sort of, the way I think about this, the difference is a little bit about, when you work in academia versus work in industry, right? So in academia, you think about, quite often about your own research topic, unless you're given it by your advisor, right? You're free to select things you want to work on, and you try to change the world. You have like these fundamental ideas, you think about broad questions, and in some sense, what you do eventually will bring value to the society, to humankind, but in sort of long-term future. If you work in industry, the story is very, very different. You start thinking about applied research, about very practical applications, and it is business problem driven. So quite often you not have the freedom to actually select what you want to work on, right? Every business has its own problems they need to solve, and you becoming part of that solution. And of course, the idea here is you're working on the direct value. So whatever you do has to bring value to business in the near future. Maybe not immediate, but quite close. And if you think about results, what's the result of academic work? Yeah, it's publications, right? That's ultimate result is, creating new ideas and then spreading them around. So, then you're judged by publications. Whether it's good or bad, but that's a fact of life. In industry, it's of course typically about successful projects or products that have been developed. And of course, when you work in academia, you have certain timelines, right? But very often your timeline is your 5 years and PhD program, right? So you need to do something, and you need to get your dissertation in 5 years, or maybe in 2 years in masters, or maybe there are some deadlines for publications. Quite different things happen within industry, where you have very strict deadlines and very strict sort of timelines you need to satisfy. If you think about who is actually working on the project, it's usually you, sometimes with co-author, sometimes actually even bigger lab involved, but mostly it's kind of a lonely journey, right? It's you and your great idea and the topic. In industry, it's always about team effort, and it's not just words. The reason is because when you want to get your code or your algorithm running, it's usually running within a big ecosystems and solving particular business problems. And so within your team, there will be business people, there will be software engineers, you will be responsible for algorithms, there will be marketing people, etc., etc., etc. So that's a big team, and in fact, the word that within academia you kind of hate, which is a process, right? So how you do sequentially things, it's actually king when you try to execute a project within the industry, because a lot of people involved, and you need to sort of coordinate and choreograph all that. And there are a lot of other things. One, I think, important part is also that in academia you quite often work on either smaller data sets, or sometimes it's already prepared, like for Kaggle competitions, or you actually generate data set believing that, hey, I have this pure data, I will add Gaussian noise, that's like the real stuff. Well, it's not. In industry, you literally spend 80% of your time, if you work on the data-driven projects, on actually cleaning, collecting, understanding the data. And just so far, there is really no way out of it. And in fact, those startups that will manage to create products that would allow to clean and merge and contextualize data, they have very, very big future within industry. So speaking about, again, industry, there is like a lot of flavors. There was like industrial R&D labs, which, somewhat closer to academic story. Then there is obviously BI analytics. There are engineering teams, and you can be part of it. And there is, the new flavor is a data science team, which is usually asked to solve business problems using, all kind of data science approaches. So that's the way I think about sort of industry versus academia. I'm sure there are like a lot of other differences, but I would say the biggest thing that impacts you if you decide to do it, at first you're working, the result of your work is product, second you work as a team, right? Those are two biggest things that completely different from sort of academic world. Okay, so this is a pure consulting slide, right? So that's what we usually come to our clients and talk about when we talk about digital. The reason I brought it here is just to show you different industries that are out there that in fact using machine learning and data right now. So probably media, logistics, mobility, retail, those banking, telecoms, they are pretty advanced right now, and they have moved pretty far. They're already using a lot that has been developed within academia. What's also interesting is, so real sectors industries, right? So it is energy, it is construction, it is manufacturing, it is oil and gas, which is part of industries. Over there is a huge field of opportunities, because some of those industries, they have lots of data historically collected, plus today there are tons of sensors installed everywhere. And that data is being collected and not used that much. And so as an applied researcher, those sort of real sides, real parts of the economy, that's actually a very interesting topic right now, right? So if you try to publish a paper on cats and dogs, well, there's like 10,000 papers on cats and dogs, right? If you try to publish a paper on trying to predict if, I don't know, gas turbine is gonna fail, okay, there'll be like 5 papers like this today. So all of a sudden, people start reading because there is not that, it's not such a, the field is not very competitive yet, right? And it's ripe for applications of modeling. Now, I think this is also quite interesting slide. Here I'm talking not about industries, but more about very specific topics you can think of. And probably working in industry, one of the key skills as a data scientist is being able to convert business problem to an algorithm, right? To actually think how to solve it. What algorithm you can do, what data you need to have to solve it. So, Verily? Okay. So for example, if you think about customers, and this is more towards, say, retail, right? One of the biggest challenges right now and sort of products, you can build what's called personalization, which is what type of offer give to a customer at a particular time and what to actually offer, right? So you want to predict the probability that the customer will accept certain offer at certain price point at a particular time of the day, right? So that's sort of a formulation. Cross-sell and upsell is, you know, somebody's buying something, what else can you sell to them? Again, you calculate probability for different items to be purchased by this customer. Churn and retention, this is a huge topic. You know, every consumer business where acquiring consumers is expensive, like banking, like telecom, wants to keep those customers, but they churn out, they can go to the competitor. And so the question is, can you predict when the customer is going to leave, right? So churn out. Now, interestingly enough, then you start thinking, okay, well, if I want to do this, how can I formulate this as a mathematical model? Well, what you can say is, let's take next month and say, and have a binary solution, if it's going to churn out, if the customer is going to churn out or not, right? 0 or 1, that's your classification problem. Or you can try to say, well, can I predict actually time to the event, time until somebody churns, and then it's regression, let's calculate, let's say 30 days or 40 days, whatever. Interestingly enough, if you see enough industry, you realize that what I just described, it is very, very, very similar to the description of what's called predictive maintenance in operations, where you try to predict time to failure, where you have equipment operating and you want to calculate if it's going to fail within the next 30 days, or if it's possible to predict, you know, precisely like 30 days or like, you know, 50 days to failure, time to failure. It's just called differently. But after you take the business problem, convert it into analytics problem, the way you're going to use it, the algorithmic approach will be the same, right? Okay, and then there is a customer experience, acquisition, etc., etc., etc. If you think about products you do, of course, it's about, for example, it is pricing. Now, pricing means what price to give to a particular item, you know, in the store in a particular time, such that it maximizes total revenue for the retail store, right? It's an optimization problem. Promo effectiveness. That story is you give promotions, right? The question is how efficient it is, right? So you might lose money on it, or you might make money because customers buying much more stuff. Seems like a very simple problem, but since you work within the entire ecosystem, there are a lot of other things that might change, for example, your approach. If you think about this, let's say, you know, there is this promo given on a particular item in the store. What other sort of external factors do you need to take into account to understand how well it works? I know this is not about math, this is about a little bit more about business, but just try to use your sort of everyday, you know, experience. When you see something on sale in the store, what affects your decision to buy it or not? Well, first of all, do you need this item whatsoever, right? But then, there are some items you can buy ahead of time. I don't know, think about toilet paper. Yeah, you can buy just, hell, as much as you want. But bread, if there's a big discount on bread, are you going to buy lots and lots of bread? No, right? So different types of products, because they expire, you're not going to buy them. Now, if you spend some time on a particular, if there's a discount on a particular brand, and you as a customer buy it, there is always competitive brand standing next to this one, which means the sales of that will decrease. So again, it will affect the bottom line. So there's a lot of factors you need to take into account if you want to build the model of how efficient your PROMA is. And I can go through like all of those things. It probably doesn't make a lot of sense, but I think there are a few interesting points is like, for example, energy efficiency, right? Is how do you optimize the usage of energy in a lot of manufacturing. Like for example, steel manufacturing, that's probably major cost is an energy that goes in there, right? So how do you optimize production to minimize the cost based on energy prices? To solve this, because the production, you cannot change the volume of production instantaneously, you need to be able then to predict what the demand would be and what the cost of the electricity will be, say a few days or weeks in advance. And based on that, you can optimize your production schedule. So it's a forecasting problem in the first place, right? And then an optimization problem. And so you can go through each of those sort of topics and think of different combination of various sort of approaches, how to decouple them, decompose them into pieces, and each of them will be either machine learning problem or optimization problem. Okay? And by the way, guys, again, if there is something you want to dig into, just stop me and I'll be happy to talk about this if I know the answer, and even if I don't. So, problem solving. You know, within academia, and again, I don't want to generalize, right? But I remember my own life in academia, and quite often I have this great idea, I have this terrific algorithm, it works, then I go and look what can it solve, right? So I have this hammer, and I want to solve something with it, and I'm looking for a few data sets that I can actually show that it works, and then I can publish it. Or sometimes, I heard something somewhere, and then I'm trying to do it, and then I'm chasing the data. Within business environment, the story is very, very different. So typically, it all starts with a business problem. As I said, you want to reduce churn, or for example, you want to prevent failures of the equipment, right? Now, why I keep coming back to the failures is just simply because, been for the last year working a lot on those topics, and there is big money involved. I will give later an example of an oil platform, and I actually talked about that example last Saturday. I'll just cover it from a little bit different angle, but so you would understand, an oil platform typically produces, $1 million worth of oil within 3 hours. So if something breaks down and the production stops, it's $1 million loss every 3 hours, okay? So if you can solve that problem, and if you can predict the breakdown of equipment, and hence, there is a question, of course, can you prevent it, right? Or can you actually minimize this downtime? That's a lot of money. And so again, when you think about the sort of problem solving in industry, it's really about, money, right? Let's face it. So you have this business problem. Then you try to formulate it analytically, like we just did, like sort of decompose this into pieces that you can actually approach from an analytical perspective. Then you start thinking about algorithmic solutions, so how you can solve it algorithmically. Then you build certain proof of concept. You see if it works or not. Then you build what's usually called minimum viable product, right? So sort of the product with a minimum number of features. You deploy it live, and then there is always the sort of changes in business process, or change management, the way we call it, is just making people use it, because your algorithm is useless until actually business start using it, and you start seeing sort of money or anything else from business, right? And as I said at the beginning, if you are within industry, process is a king, right? And so if you notice here, you're part of this sort of this pipeline of decisions that are being made. Now, again, I can talk about like a lot of details on how we sort of, for example, can build this prototype, how how it is different from the product development and this industrialization phase. But the point is, as a data scientist, as a machine learning expert, you will participate in all those steps. But the participation will be different. At first, you actually spend time, trying different solutions, trying different algorithms, seeing if they work, right? When you finally find something that more or less works, you try to package it with the help of software engineers, put it into the product, connect it to the live systems. And then, if that happens and you're successful, then you go into industrialization. Now, to be honest, there's lots and lots of prototypes being always tried. There's much fewer products being built, and there is very, very few things that successfully being industrialized, right? So it's kind of a funnel. But you work in all those pieces. Any questions so far? No? Okay. Yes? Mm-hmm. Uh-huh. Right. Are you a lawyer? So look, that's actually very good. In fact, it's a very, very good question. And so what you do, and this is, we're jumping a little bit ahead of time, but let's say, and we'll get back to this question, just remind me about it, but you actually can calculate the risk, right? So you can actually put a monetary value to the risk, and you can evaluate knowing of course, your algorithm is not perfect, right? We always keep telling like, okay, there is this precision, recall, right, accuracy, true positive rate, false positive rate, etc., etc., etc. So if you missed an, if you missed an event and it happened, it's certain cost associated with it. So you have a probability with your model that you're going to miss an event. So you can expect, you get an expectation of the cost, and so that's what you do. You kind of compare what's going to happen if you, deploy the model or not. Uh-huh. Yes. So it's up and loads up and it doesn't work exactly like that. Of course, everybody tries to minimize failures, right? People take responsibility, but yeah, eventually, you decide if it's worth trusting the model, right? I mean, there is all these questions. Self-driving cars on the street, it's going to hit somebody, right? Who is at fault? The passenger, Yandex, I mean, those who create the self-driving car, the car manufacturer. So there's, it's a Pandora box right now, right? So if AI or machine learning algorithm makes a mistake, who is responsible? And in fact, as far as I know, there is really no good solution so far in terms of like, there is no laws that control that. But in real life, what happens is there are certain costs that being associated with maintenance, and certain costs that being associated with breakdowns. And then there is, and it's a managerial decision, right? And it's usually top management, whether you want to change the schedule of maintenance, understanding that you're saving that money, versus there is this possibility of breakdown, there is this risk, but then there is insurance companies. So that's what I'm saying. It's all sort of within a bigger picture, but it's a good question to think of. Okay, so yeah. Okay, so the question is, there is sort of preventive maintenance that happens during the on scheduled intervals, and that should prevent from breakdowns, right? Well, I can ask you. Well, you go to dentist regularly, right? Probably every 6 months, but there's still some problems happen sometime, right? And so, in spite of preventive maintenance, problems do happen. Now, how do you manage this preventive maintenance schedule? The idea is with a predictive maintenance is going away from regular scheduled maintenance, or maybe change the time interval between them, for example, increase, and then monitor the condition and do the maintenance when needed. So for example, one of the big cost factors in the real industry is that you do maintenance when it's not needed, right? For example, you have scheduled maintenance on your car every 3,000 miles, you need to change oil. But if you don't drive if for example you drive it, in the city or on a highway, you might not need to change it every 3,000 miles. You change it when you see that the oil is either low or it's dirty, right? If you drive your car in the desert, that's a very different story. So maintenance depends on the usage of the equipment. And that's sort of what this story is about, right? Try to understand the condition of the equipment, try to predict if the failure is going to happen, and base your maintenance out of those observations and those predictions. Oh, okay. Oh, yeah, so that's a very good question. So, first of all, failures do happen, right? And sometimes you do observe those events. No, not necessarily. I mean, there is a well-maintained equipment that fails once in a while. I mean, if you have a car and you maintain it, once in a while your tire will blow out, right? And so you might actually notice that the temperature maybe changes within the tire, or sometimes your brake wear out. So that happens. But the question is actually very interesting. The question is that, we're sort of jumping ahead, but that's fine. If you have the problem of predictive maintenance, predicting the failure of equipment, quite often you do not have enough training data, the events of the failures themselves, to train on, right? Because if you want to predict something that something happens, you need to have examples of that happen, right? And let's say if you're talking about consumer goods where you have, customers, millions of customers in the bank, thousands of them churn out every month, so you do have a lot of statistics on the events. On the expensive and large equipment, you don't have that statistics. That's very true. So, options are, we actually do a lot of anomaly detection because of that. So we're not predicting time to failure, we're not looking into supervised learning, we are looking into unsupervised learning solution, right? Trying to just see, we learn, we do anomaly detection through what's called one-class classifier, right? Where you learn one class, which is healthy behavior of the equipment, and then you classify every time step as being healthy or unhealthy, and use it to do anomaly detection. That's one option. Another option, there would be, you can do transfer learning, right? So you can actually try to learn on different equipment and then use that, sort of have a pre-learned models and then just train them a little bit on your equipment with, single failures. There are one-shot classifiers, you can try to do that, which is learning by one or two examples. So there are techniques around it. But honestly, we try like a lot of things. Right now, we do recommend mostly anomaly detectors because they're the most robust. And this is something actually I also want to talk about a little bit, that the algorithm that you want to use in industry, they have to be robust, right? So which means if distribution changes a little bit or something changes, it still should work, right? Anything else? Yeah. Right, so we usually like sort of this minimum viable product, that's where we talk more about software development effort. But yeah, you're right. I mean, again, you can take this and dig deeper and put many more sort of sub-steps in here. The goal of this slide, guys, was just to show that your algorithms is actually part of the process, the part of the bigger process. It's not a standalone thing that you wrote for your thesis or for the paper, and then you forget about it, right? It's a part of the bigger sort of chain of events, right? And you should understand what's happening sort of upstream and downstream from it. Okay? All right. Yeah. So if you think about models, and then this is sort of modeling 101, and tell me if it's boring and it's very much familiar to you. I just want to give like a highlights of a little bit highlights of things here. So when we approach, let's say we have a business problem, so we know how algorithmic problem works, we know what to solve. Now the question is what algorithm to choose, and then there is this question of selecting algorithm. Then there is a question, of course, of feature engineering. Then the question of training, testing, validating. Then the question of, okay, well, can we actually optimize things that work that they work well. And today we actually do a lot of model stacking just to make it more reliable and pull a little bit more out of the results. Now, if you think about algorithms again, this is sort of the cheat sheet that we use. It's not, of course, the ultimate truth, but the idea is that in algorithms you can think about things like when you have a time series, right? You deal with forecasting problems. Sometimes things like moving average, ARIMA type of approaches, and that's what happens when you don't have a lot of features, right? And you just have one signal that changes with time, and you try to predict what's going to be happening. Now, let's say if I do demand forecasting, usually there are features I use, so that might not be the right thing. But sometimes, if for example, you have one single sensor on the equipment, you might want to forecast it just based on the sensor itself. Then the next kind of group, which we call point matching algorithm, but that's really classification or regression, where you have samples of points and you take your sample and you just try to see, if it is close to any of the data points you have, right? And that's again, all the world of regression classification problems. When you have some knowledge, some priors about the process or the problem you want to solve, or when you have fewer data and you want to put a little bit more knowledge into the play, we think about Bayesians, using Bayesian approach, and then of course a lot of deep learning, but I will be very careful with the deep learning these days. It works terrifically well on certain type of problems, right? It works tremendously well on image, on text, on sound. It doesn't work that well on many other problems, right? And there might be multiple reasons, and I'm sure you have heard on the lectures here why that's happening, and it requires a lot of data. And sometimes in real life you do have it, sometimes not. But retraining can be expensive. So there are a lot of things, a lot of constraints that prevents you from using deep learning, right? But there are some problems where you use them and use them a lot. You use it a lot. So what I'm just trying to say, you have to be kind of careful and understand what resources you have, what data you have, the goal when you're selecting the type of algorithm you use. And of course, the big question is about feature engineering. And in fact, here in industry, the difference probably between academia and industry is that in industry, you do have access to the experts. So if I want to build a predictive model that this particular pump or this particular turbine is going to fail, I will actually spend weeks with the maintenance manager, with the maintenance engineers, trying to understand what they're looking at, what signals they're actually investigating and how they do it, right? I mean, sort of obvious from physics. Okay, you take vibrations and then you do, for example, Fourier on vibrations, on vibration sensors, and then see if there's any new harmonics appear, and that's your rotating equipment. Will signal failure. But there are temperatures, right? There are pressures. Then there is incoming flow, outgoing flow. So there are a lot of things that might affect the performance. And you're not going to learn it just by looking at the data. You actually have to go and talk to the experts. And that's sort of the feature engineering part. Now, of course, the dream is, if you think about deep learning, we just send signals in, and it's going to learn on its own how to combine things together, right? So you don't need to do feature engineering. Deep learning will do it for you itself. Honestly, it's not happening, right? So the feature engineering is still there, and it is you have to have domain knowledge to do it, right? And that's where sort of integration with experts priceless, right? Okay. Then of course, when you build models, here is your, you define the target, and depending on what target, what you're optimizing, depending on the problem, you need to select different type of measures, right? So for example, whether you're concerned about outliers within the model or not, right? That sort of dictates the type of measures you choose. The same with classification, and here I want to stop for a second because that comes back to your question about the failures, right? I'm sure you have seen the matrix, right? And you have seen ROC, you know what ROC curve is, right? So the question I would normally ask at when we interview people, everybody knows about ROC curve and the quality metrics, right? AUG, ROC, right? So your algorithm can work anywhere along this ROC curve, right? Because you can select the threshold and you'll have different true positive versus false positive rate. Okay? So that's sort of in your control as a modeler. So how do you select the right point to work at? How do you choose the point along the ROC curve where your algorithm should work? Speak up, please. Exactly. To answer that question, that's where you need to look at the environment and decide, okay, look, if I have this matrix for true positive, false positives, what does it cost me, right? So if my algorithm makes a mistake and misses the event, what are the consequences? Versus if it's gonna, create false positive and then call a failure when it's not, right? And it can be very, very different price points because think about your car alarm versus, I don't know, top security system entrance into military facility, right? So in one case, what's the cost of false positive versus false negatives? And so what you do, knowing that cost, you actually, knowing the cost, you group it together, right? And you try to, and then you calculate the expected loss, due to your model, and then you choose that point on ROC curve. So all of a sudden, the pure analytics or data-driven thing converges with economics, right? Typically in academia, you don't care about that, right? You have the great area under the curve, you're done. But when you use it in practice, you actually need to select where on this curve you need to work, your algorithm will work, and that's sort of where consequences comes in. Make sense? Okay. And I can talk about like a lot of different things, how to do, for example, test validation set right or wrong, in terms of if you have like different users and different time domains, how to split it and not to split it. Some of those things are kind of quite easy to understand. Others, requires a little bit more in-depth thinking to make sure you don't have like signal leakage from the past into the future, et cetera, et cetera. So I will skip a few slides. I'm probably out of time. Sort of final thoughts, and then I'll show a few examples, and feel free to ask questions after that. So first of all, from sort of experience in industry, Occam Razor. How many of you are familiar with that? Okay, so can somebody tell me what it is? Well, I have it there, but in your own words. It is if there are different solutions explaining your problem, select, choose the simplest one, right? There are different explanations. I mean, okay, there is probably the original wording is very different, but the way we use it, right, is out of, if you have some event and there are different ways to explain it, the most likely is the most straightforward explanation, right? So if you have different models that explain the data, choose the simplest one. And honestly, in many cases, it can be linear regression. I mean, as an academician, it's embarrassing. You worked here for, you spend your life in academia, you got your PhD, then you come to predict failure of very expensive equipment, and you tell them like, okay, I use linear regression. 5 coefficients, and hey, that's it. But in fact, quite often, this might be the best solution. It's the most reliable and explainable. And by the way, when one of the things which I forgot to mention here, your models has to be explainable if you want people to use them. They need to understand what is actually happening. For an engineer to understand your black box deep learning model is not possible. They just say, okay, like which sensor and like sort of where do I need to look at the problem? So they want some explainability. Now, of course, you can use deep learning and try to build explainability around them, but that's a different story. Now, this is a very famous quote that more data beats complex models, right? I mean, I think it originated in like late 90s with Microsoft researchers that looked at the different NLP problems. But this is absolutely true. If you have an option to collect more data and use simply algorithms, that's the way to go versus sort of other way around. Now, another thing, you kind of keep forgetting if you work not in industry but in academia, that you usually have a data set that is given to you. You got it from somewhere. You sliced it, you diced it, you trained on it, you verified on it, you tested it. I mean, life is good. Well, the trouble is when you deploy in real life, things might be very different. The distribution might shift during, the distribution of various features most likely shifted, and so your models just will not work the way they work on historical data. And so, it's not done until it's validated live online, right? Again, thinking about equipment, you build on historical data, but they changed a little bit the processing line, or they made the major rebuild of equipment, and the signatures of failures would change. And so you have to retrain. And so this historical data is not going to work anymore. Now, model, the one you built, is going to be part of the bigger ecosystem, and it's not something, it has inputs and outputs, and it's connected to this world. And if something changes in that world, you might need to adjust your model. And finally, it's actually not done when it's done. Like in academia, you publish the paper, you are done, right? Then, if it is accepted, 6 months later, you might go back and try to put slides together for the presentation, but that's sort of how it works. You'll dig out your code and you'll say oh well, who wrote that? But that's fine. In academia, in industry, if you actually build a model for production, you have to support it, right? It's your baby now, you have to grow it, you have to nourish it, you have to support it. And that's sort of a big difference in the mindset. All right, now we have probably, Evgeny, can I have 5 more minutes? 5 minutes. All right, I have 3 case examples I can go over. Actually, 2. One is talking about personalization and the sort of how we do personalized offers. Another is talking about oil platform and predictive maintenance a little bit. Which one? Both. Okay. All right, but it's going to be quick then, and if it's interesting, we can talk a little bit after that. So this is a Starbucks story. This is a real story. We actually did it, and this is the cases that as a BCG we worked with the clients, and we did it. In fact, if you're a Starbucks user, if you drink Starbucks coffee, and if you're a member of their loyalty program, most likely using some of the algorithms that we have developed several years ago. And the idea over there was to actually create personalized discounts or personalized messages or personalized combination of products that you offer different clients. And when we came there into Starbucks, they had probably 30 different types of offers they're sending out to all the people, to all their loyalty program members. And then we kind of tune it up. So they send out more than 500,000 offers right now, and they have 20 million clients. And then the measures from the business side was, of course, the way people react onto the offers, right? And the reaction on the offers would be either you actually come and buy it in the store, or sometimes it's, the marketing measures, for example, the click-through rate on their ads, right? So if you send an ad, if it's been opened, clicked, etc., etc. So probably an interesting thing is to understand that the big brother is watching, right? And the big brother can be even the coffee shop. So Starbucks knows a lot about you. This is a dashboard we help them build about your coffee habits, right? If you have a loyalty card and you use it, and that's not only, of course, Starbucks, every store, think about airlines, how much they know about you. You can actually see what type of purchases being done, right? And at what locations. Now, without even being sort of deep analyst, without using any deep machine learning, if you see that somebody buys coffee there on Saturdays and Sundays, what do you assume about where they live? Well, they live next to that place, right? And if they show up at other locations, during the week, you can, for example, if those locations scattered around, the person could be, traveling salesman, right? If the locations are kind of always the same, okay, that's where his office is. So even from this simple data, you can figure out a lot. Or if you see a lot of loyalty cards appearing one after another, time-wise in the same location. Well, you get your social network, you know who is friends with who, because they keep purchasing together on different dates, right? Again, think airlines, they know, you fly with groups of people, et cetera, et cetera. So there are a lot of information in there. Of course, they know what person bought, when they bought, how they like their latte, non-fat, decaf, iced, whatever. All right, so you can actually look and try to build what we call trajectories, which is a customer engagement, so how often they engage, and for example, what you see here, this is color-coded, in increasing trajectory, like getting darker, it means somebody is actually using more and more and more coffee, which is good for Starbucks, right? And then, for example, like the decreasing trajectory is somebody getting off this needle. And there are multiple of models, and this I think probably the most interesting part of the story, the type of models you can build, right? So first, you pick a random person and, taking his profiles from social networks and try to calculate probability to sign him up for a Starbucks loyalty program, right? If we send him this $20 discount, if he's gonna sign up, right? And the question here, the cost here, if maybe he would sign up without this $20. So then I just wasted those $20. So you try to predict if somebody is ready to sign up just because I would say, hey, I'm Starbucks, go join my loyalty program, or for somebody else, you need to spend $20 to get the guy. Then there is product propensity, what type of product they're going to buy in Starbucks. There's cross-sell, upsell, you always buy coffee. Maybe you should try the bagel, right? But if somebody buys non-fat, whatever, latte, what's the chance that he will buy, I don't know, some fat bagel or fat burger? Oh, very little chance. But if somebody is so health conscious, you probably can push more health conscious products. There are even more interesting stories like these headroom models. Those are the models trying to predict how much more we can get out of this person. The way it works is, of course, you find people similar to the particular customer and see how much they spend. And you realize if they spend more or less than other people like him, and that means, okay, there's a headroom to push more. And one of the ways to push more is either to offer different products or, sort of ingenious tricks, like if you always buy cheap coffee, right? And Starbucks wants to sell you espresso-based drinks, what do? Well, they offer you a couple of discounts or get, for example, latte for the price of dripped coffee. And guess what? The person is hooked, right? And so then they start spending more money. So there are a lot of things you can actually do knowing those profiles of the customers. And again, just sort of big picture, for every, and what you see here, user IDs, that's actual IDs, well, I mean, this is not actual IDs, it's hashed, but those user IDs, the type of products they buy, and those are computations of engagement score, so how often they buy, the risk score of them leaving and stopping using the Starbucks headroom, which is like, okay, we feel that this guy is already like spending all his money, or hey, we feel that people like him actually spend twice as much. Like we can push a little bit more of product towards him. And though this is, Starbucks story, this is very, very typical for a lot of, consumer goods and a lot of sort of stores. That's how they, go after the client. And then, of course, it's connected to web apps, et cetera, et cetera. Okay, that's sort of one story. And I'll be happy to give you details, if you still buy it. Another very different story is very popular in the industry right now is this whole digital twin, right? Where you want to have sort of some type of simulators where sort of traditionally there exist a lot of physically based models, right? That may predict certain events, whether it's at the process industry, upstream, downstream, chemicals. Those models, unfortunately, not very precise, and the reason for that is there is a sort of textbook understanding of the process, and then there is a real process that's happening, and it's always again connected to a lot of things happening around it. So those models are not precise. So you might think about, okay, can I actually, if I have a data, can I actually build the models from the data? If those models will be more precise. Plus, usually physically based models, they take time to execute, right? You cannot run them all the time. And so the question is, can we maybe shortcut and go for, based on the data, sort of replace physically based models with data-driven models? And plus here, the story is, of course, optimizing production and minimizing, failures. That's not interesting. So I talked a little bit about this example we did with Lukoil a year ago. Lukoil is one of the largest private, actually it's the largest Russian private oil company, where we build a system that monitors their equipment and predicts failures. And I'll just, so what you see here, it's a screenshot of the dashboard we did. So it's a sort of MVP. I probably spend the next couple of minutes on actually talking a little bit about the model itself. So the idea is, so you have turbine, and you have a SCADA data from the turbine, and we were actually looking at the very particular type of predictions. So what we wanted to do is we wanted to try to do what's called virtual sensor type of approach. So the idea is the following. You have a bunch of sensors on the equipment. And those sensors, they measure the same equipment, the same physical process, right? So that really means that what they measure correlated. So based on what values of some of those sensors, you could try to predict other sensors. Now, the idea of this virtual sensoring as applied to failure prediction is the following. You take the stride of data when you know your equipment operates well, right? When it's sort of healthy. It's normal operations. And then you learn from the sort of machine learning meaning of the word, you learn the correlation between those sensors. So you can predict one sensor from all other sensors for healthy performance of the machine. And then you start monitoring, you do this prediction, trained on healthy performance, and you compare it to the real values that comes from the sensor. Now, if machine remains in this healthy normal state, they should be very, very close. But then, when something goes wrong and the machine start degrading, then the predicted values will become different from the measured values. Because you learn correlation on the healthy data, and so it knows how things should work together when the equipment is healthy. So that's the idea. Overall, there are different methods. You can also use autoencoders here, also training on the healthy data, so learning the weights of your autoencoder on the healthy data, so it can reconstruct healthy data. But then, when you start sending the data that shows you abnormal behavior, then the reconstruction would be worse, and that will signal for you, the anomaly. So this is, literally the anomaly detection approach. We're not trying to say, it's going to fail, in 30 days or in 20 days. We're looking at the anomalies. And here is an example of one of the situations. What you see here, and this is sort of the real data, right? Here is, several months worth of data. On the left-hand side, on this February, you will see the maintenance when it's been performed. Then we trained on the data after that. And by the way, this is a historical story, right? And then we kind of monitor, we predict the value on the sensor, right? And we monitor the value on the sensors. And if you notice, closer to like April 17th, April 10th, that's when you start seeing huge differences in between predicted values and the values that are being measured. And then the catastrophic failure happened like end of April. Now, again, this is back-tested data, so, we built an algorithm. So they came to us when that thing happened, actually, and asking like if we can, looking in the data, would we be able to predict this problem, right? And the anomaly appeared probably like here, you can see, 2 weeks before the event. Now, going back to this, to the picture, what we've done, there are bearings, right, and there are temperature sensors. And so what we looked at the values of the temperature sensors, trying to predict particular values from others, and also from, the usage of the turbine. Yes. Yeah, because there are a couple of things. We want to completely avoid any of signal leakage, right? And so the gap could be quite small. And then we also wanted to give an advance warning, because if you do train and predict next to each other, it really means, you know, you will notice problems. Your problem can happen from this end of the predict interval to this, which is sort of today, because you can train on, when you do multiplier, it shifts and starts at every day. And so what you want is you want to be able to predict a little bit into the future. No, this is it's being trained. So you start with training offline, but then this has been done online. So you retrain the model, and then you apply it constantly. We can talk about this a little bit more when we're done. And I think I'm out of time. You know, thanks guys, and feel free to ask questions. I hope that was sort of entertaining enough to keep you awake before lunch. Done.